My name is Mototsugu Hamada with Keio University. I'm talking about padless chip-scale RFID. This is the outline of my talk. I'll start with the motivation of my work. Then I'll propose a new RFID tag system. Then I'll talk about circuit details of 3 key components. Then I'll show you the experimental results. Finally, I'll conclude my talk. Let me start with motivation. Left-hand side is a typical RFID tag system, which consists of tag and a reader. Tag stores ID and a reader recognizes its ID for authentication. Right-hand side are small electronic components. The traceability of small electronic components are an issue now. Then, the miniaturization of RFID is very necessary today. To miniaturize RFID, we have to miniaturize antenna since the size of antenna is the size of RFID tag. To miniaturize the antenna, we have to use on-chip antenna with a higher frequency band. At this moment, we will face 2 design challenges. The first one is the loss due to the free space channel. The loss increases with a higher frequency. Another challenge is the loss that increases with on-chip components. On-chip components are lossy when it is on-chip compared to the external components. The communication distance decreases with decreased chip supplied power. Now I will propose a new RFID tag system. This slide shows a standard RFID tag system, which consists of power converter, clock generator, ROM that stores ID, and control logic, also with load modulator. Since the CMOS control logic requires a constant DC supply voltage, it is driven by wireless power transfer using continuous wave like this. This slide shows proposed RFID tag system, which consists of RF to envelope power converter, ring adiabatic shift resistor, and load modulator. It is driven by wireless power transfer using off-keying wave for adiabatic logic. RF to envelope power converter generates duty-cycled power supply. By doing so, we can reduce the average feeding power. Also, the adiabatic shift resistor is low power owing to its adiabatic operation. Besides, we don't need large capacitor to smooth the output of wireless power transfer. The circuit size can be small. Now, I'll talk about 3 key components detail. The first one is adiabatic shift resistor. This slide shows the example of NMOS type. It operates with non-constant power supply like this, which we call power clock. When power clock is high, it precharges output. Both of the output goes high. When power clock falls, it evaluates the input. For example, if INP is high, MN1 and MN2 discharges the node of out N. So out N falls, while out P remains high. Like this, this circuit operates with the falling edge of power clock. This slide shows PMOS-NMOS adiabatic shift resistor. It's a combination of PMOS type and NMOS type. Similarly to the NMOS type, we can implement PMOS type adiabatic shift register. By combining NMOS and PMOS adiabatic shift register, we can construct a shift register driven by single-phase power clock. By cascading PMOS-NMOS adiabatic shift register, we can implement memory function. This is an example of 4-bit case. With the power clock, we can have the output according to the connection between PNASR. In this case, we have straight connection and cross connection. Straight connection corresponding to the non-inverting connection. Cross connection corresponds to inverting connection. We can have 1, 1, 0, 0, 1, 1, 0, 0, and so on output by the connection of cross-straight connection. We can have unique bit sequence depending on the connection. In this case, we have 16 combinations. If we have n-bit ring shift registers, we have 2 to n combinations. This is the on-chip antenna design. It has a dual loop structure. It's very small compared to the wavelength of the operating frequency. In this case, it's about 5 GHz. It is conjugate matched to the input or impedance of RF to envelope converter. This slide shows the performance of the on-chip antenna. It has a maximum gain of minus 26 dBi at 58.8 GHz. This slide shows RF to envelope power converter. It's a 6-stage CMOS cross-coupled charge pump with a resistive load. When input power is minus 10 dBm, we can have 1.8 volt that is operated for the CMOS logic. By duty cycle of the duty ratio of 0.1, the average input power is minus 20 dBm. This slide shows full chip simulation results. The duty ratio is 0.1, data rate is 10 kbps, input power is minus 20 dBm. As you can see, RF in, the level is 100 mV. RF to power converter boosted it up to 1.8 volt. And we can have the radiated power corresponding to the stored ID 1000 or 1001, like this. Now I'll show you the experimental results. This slide shows the test chip photo. As you can see, the size of antenna is 1.2 mm by 2.1 mm. The size of core circuit is 0.3 by 0.3 mm. It is 0.18 micron standard CMOS process with the thickness of 150 micrometer. This slide shows the measurement setup and its results. We have a signal generator here, transmit antenna here. The distance between the antenna to the RFID is 10 centimeters. We have a different antenna here to detect the irradiated power. On the left-hand side, we can see the TX signal, and we can monitor the ID outputs for test purpose. Here, the pattern is 11001010. At the irradiated power, we can see the amplitude corresponding to the stored ID. As you can see here, 1001, 1010. It is capable of 10 kbps at a distance of 10 centimeters with 24 dBm EIRP. This table shows the performance summary. FOM here correspond to range over squared root of area and EIRP, which means range normalized to size of ID and radiated power. As you can see, we have the highest FOM compared to the conventional ones. Now I conclude my talk. A padless chip-scale RFID tag is proposed. It operates with overgate power with a very small size antenna by using adiabatic logic. It is capable of 10 kbps at a distance of 10 centimeters with 24 dBm EIRP. These are key differences. Thank you.